So the first thing that I think of when I think of dilations is something being made larger. So one thing you may have heard before if you've been to the eye doctor is they dilate your eyes by putting drops in it, making your pupils bigger. Or if you've ever done that game in elementary school where you had to look at someone's eyes and they turned the light on and off and it made their pupils bigger or smaller, that's dilation. If something is just growing in size. So first let's fill out some of these notes. It says, for a description, a rule, or like a definition, that the figure enlarges or shrinks with respect to a fixed point. And what we do is we actually take all of our ordered pairs, x, y, so any number, maybe 1 or 2 or 4 or -3, whatever our value is, and we multiply it by whatever the number is that we want to enlarge it. So if we want to make it twice as big, we multiply it by 2. If we want to make it half the size, we multiply it by 1/2. And this number, the k, has a special name. It is called the scale factor, or you may hear it called scalar. So let's look at an example. So first thing that I do when I see this is I read to make sure I know that it's a dilation. This one's pretty explicit because it says draw the image after a dilation having a scale factor of 2. So I know that scale factor means it's going to scale by that size. So think about, usually I can relate this back to maps that we do in maybe history class, or if you're looking at a map on Google or something, and it is scaled by a certain amount. So maybe every 1 inch represents 10 miles. That's a scale for a map. So this is kind of the same thing, the same idea of scaling by a number. So scaling by 2 just means that we're going to take each of our values and multiply them by 2. It's going to get twice as big. So our new thing will become a prime, and then we'll take 2 and multiply it by 2, and I'll get 4. And I'll take 3, multiply it by 2, and I'll get 6. And then I remember that I want to keep in mind that this came from the point A, so I'm going to write A prime, because I can't name it A, I already have something named A, but I can name it A prime to help me remember that. So next I'm going to do B, I'll have B prime, and I'll take each of these values and multiply them by 2. So 3 times 2 is 6, 1 times 2 is 2. And then my last point is C, so C prime, 1 times 2 is 2, 2 times 2 is 4. So now what I'm going to go do is just basically plot these points over here. So I've got A prime is going to be at 4, so 1, 2, 3, 4, 6. 1, 2, 3, 4, 5, 6. I'm going to label that A prime. B will be 1, 2, 3, 4, 5, 6, 1, 2. B prime. And C prime is 2, 1, 2, 3, 4. And then all I've got to do is connect the dots. So a couple things I notice about this when I draw it. It looks like it is twice as big as my original. Now I'd have to do some measurements to prove that to be true, but it does look like that. But it's also getting further away, and I notice that it's getting further away from the origin. And it almost looks like if, let's see, maybe I'll look at C. If I kind of count how to get to C from the origin, so let's say up 2 and to the right once. If I do that exact same pattern again, up 2 to the right once, I get to C prime. So if I do the pattern once, I get to C. If I do the pattern twice, I get to C prime, and that's because I have a scale factor of 2. So this figure is actually twice as far from the origin, and it's twice as large as the original. So let's look at an example where it is 0.5 as our scale factor. So I'm just going to take all of my numbers, just like I did in the last one, and I'm going to multiply them by 0.5, or 1/2, because it says a dilation. It tells me my scale factor of 0.5. So I'm going to say M prime multiply these by 0.5 or just take half of them because I know this is the same thing. So negative 3, negative 2. A prime will be negative 1, negative 2. T prime, negative 1, negative 3. H prime, negative 3, negative 3. And then just like I did before, I'm going to go and plot these points. So I'm going to do M prime is negative 3, 1, 2, 3, and then negative 2. M prime. A, negative 1, negative 2. A prime. T prime is negative 1, negative 3. So T prime. And negative 3, negative 3 is H prime, and connect the dots. Notice this is a really tiny rectangle. Fill it in so we can see it a little better. It's really, really tiny, and it makes sense because I am taking half of it. So in this last problem that I did, I was multiplying it by 2. I was making it twice as big. Now I'm only making it half the size, so it is getting smaller. I also noticed that it looks like it's getting closer to the origin. So originally this one was this far away from the origin, so maybe let's look at the pattern of how far away it was. So let's pick one of our points. I'll pick A. If I start at the origin, the pattern I might follow would be 1, 2, 3, 4 down and 2 to the left. Well, what if I cut that pattern in half? Instead of going 4 down and 2 to the left, what if I go half of that, 2 down and 1 to the left? 2 down, 1 to the left, and I'm at A prime. And so that means that it's now halfway from where it was in respect to the origin, and that's because of the half. So I want to think about some of the properties really quickly of dilations. So if we look at the pre-image and the image of both of the figures that we have done here, so remember the pre-image, I remember that because pre means before, so it's the image before I did a dilation, and then the image is the actual image after the dilation. So with respect to each other, they are not congruent anymore. In the past transformations we've seen, they've been congruent. So these are actually going to be what we call similar. And that means that it's almost like one has been shrunk or one has been enlarged, but they are similar, they are no longer congruent. So corresponding angles within these, so for example, if I go over to my triangle, corresponding angles might be this angle C and this angle C. Corresponding angles, we could do some measurements and stuff, but they're actually going to stay the same, even though the shape is getting larger or smaller. So corresponding angles are congruent. But corresponding sides, so this side right here, AC and A prime, C prime, they're definitely not the same size. But if I measure it with a ruler, I'll find that for the one where I multiplied by 2, it's actually double the size. So what we say is that corresponding sides are proportional. Because I'm able to multiply it by a specific number and get a proportion. And we'll talk more about that, or you'll talk more about that when you get into your geometry class in high school.